This lesson is entitled The Fundamental Theorem of Calculus. Now we're going to start this lesson by looking at a function that you see on the screen, f of x equals x squared plus 1. And we're going to look at the part from x equals 0 to x equals 1. And the range of this function is going to be y equals 1 to y equals 2. So that's the function we've chosen. It's a fairly simple function. We don't want a complicated function. We didn't want a linear function. It's for obvious reasons, but we won't go into that. But we like a simple function where the arithmetic will be fairly easy, and yet it will do the job for us. So we've chosen f of x equals x squared plus 1. Let's look at that graph. Now, x squared plus 1 is a parabola elevated to its y-intercept is 1. Okay, this may not look like a parabola. What we have is this is under the microscope. This is highly enlarged, and we want it enlarged so that we can play with it and see what's going on under the curve. You might notice that the scale differs here on the x and y axis. From my hand here to over to here is 1 unit, but yet on the y-axis only up to here is 1. So the scale is not the same on both, the uniform on the x and y axis, and that's by design. It's not going to be a problem for getting us the results we want, but it certainly will give us a visual entities that we can work with. So make sure we recognize that with you. This is an increasing function. It's important that we mention that because there's a difference, as we will allude to a little later, if this had been a decreasing function. So this is an increasing function. The slope is positive as you go left to right. And what we're interested in is we want to find the area under this graph. Now, this is not a region that you've learned in geometry. Like, it's not a triangle, it's not a rectangle, it's not a trapezoid. It's nothing we have a formula for finding the area because of this curved boundary here. So that's our initial job that we have here in this lesson, is to explore finding the area under this graph. Now, what we're going to use is something called the left-hand method. There are several techniques for finding the area under a graph known as numerical integration. And one of those is the left-hand rule, and another one is the right-hand rule, and we're going to use both of those in this lesson, but there are others that we're not going to mention at this time. This is you using the technique of Riemann sums. We just throw that out to enhance your vocabulary here. So let's go to the next slide. What we're going to do is we're going to draw little rectangles underneath the curve. And we're going to find the area of each of those rectangles. You know, we know how to find the area of a rectangle, length times width, okay? So that's what the motive here is. Let's find something that we know how to find the area of a rectangle. Now, we're going to divide this thing up into 10 little rectangles. The reason we're choosing 10, the more rectangles, the better your answer. But if you make the number of rectangles too large, then you've got a lot of work to do. And we're not afraid of doing a lot of work. That's not why we're not going to say use 100 rectangles. 10 will get the job done for us. So we chose 10. It's a fairly nice number, and it works well with our region. Now, the number of rectangles is called n. It's called n. And this graph, if you remember just looking at it, went from 0 to 1. The starting point we will call A. A is 0. And the ending point we will call B. B is 1. Now, what's the width of each rectangle? Well, if we're going from 0 to 1 and we're going to make 10 little increments, it seems to reason that what you're going to do is the entire distance is 1, b minus a, and the number of rectangles is 10. So this is a nice number. This gives us 1/10 of 0.1. That's the width of each rectangle. Now, that b minus a over n is the star of the show. That is what makes this work. It's the width of the rectangle, and it also is the increment we're going to go over as we move, in this case, left to right on the graph. So this b minus a over n, when you're doing this technique, is the first thing. And you better get that right, because if this isn't right, if b minus a over n is not correct, game is over. But it's not hard to do. Here's a drawing of the graph, the rectangles. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rectangles. This is the left-hand method. We're going to start over here at the left side for our first rectangle. And we're going to find its area. Now, its height is f of 0, which is 1, and its width is 0.1. So the area of this rectangle is 1 times 0.1. That's the area of that rectangle. Okay. Now, likewise, this rectangle has a width of 0.1 also. In fact, all of them have a width of 0.1. The height of the second rectangle is f of 0.1. The height of the third rectangle is f of 0.2, f of 0.3, and so on. Now, the characteristic of the left-hand method, and listen closely. The left-hand method, you start at your leftmost point to get your heights. And you get the height at every increment over, but you stop one short of the right endpoint. In other words, you have a height that's here, 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 all the way up to here. See, this is my last rectangle. The height of it is f of 0.9. Okay. Now, what's the area? Well, you take f of 0, that's your first height, f of 0.1, that's your second height, f of 0.2, and so forth. Now, what are these? Well, it means put 0 into your function. So when you put 0 into your function, you get 0 squared, which is 0 plus 1, 1, that's your first height. When you put 0.1 or 1/10 into your function, you get 1/10 squared, which is 1/10 times 1/10 is 1/100th, or 0.01. Add that to 1, you get 1.01. So that's the area of the second rectangle. 0.2 squared is 0.04. Add 0.04 to the 1, and that gives you 1.04, and so on until you get up here to 0.9 squared, which is 0.81. Add 1 to that, you get this. Now, that's the height of each of your rectangles, and each of them have a width of 0.1. Well, rather than mess it up by showing everyone on 0.1 times 0.1 times 0.1, we save the 0.1, bring up the rear of the expression with it. Since all of them have a 0.1 in it, you would be able to factor that out. Now, we've done the arithmetic here for you, and this adds up to be 12.89 times nicely 0.1, which we can do in our head, which is move the decimal one place to the left. So 1.289 is the area of that region using 10 rectangles. But this is an underestimate. Let's come back here. See, we're not getting this part. We're not getting this part. We're not getting this part, this part, this part, this part, till it gets so small. We're getting this, this, this. So we don't really have the area. What we do know is that the area is probably at the minimum equal to 1.289. What we have here is a shorthand notation. Now, this is going to be very helpful to us as we journey through calculus. This notation You're hearing it probably for the first time here, I'm assuming, but I could be wrong. All I've done here is written out in other words, these rectangles start when at 0. And how far do we go up to? 1 minus 1/10 or 0.9. We start at 0 and we go up to 0.9. So this is a way of saying 0 to 0.9. This capital sigma means summing. In other words, we're going to put 0 into this and find f of 0, and then we're going to put the f of 0.1 and so on up that, and add all those. This means add them up and multiply by 1 minus 0 over 10. That's b minus a over n. Okay. Now that's a notation for the problem we are working on. But suppose it didn't go from 0 to 1. Suppose it went from 5 to 9 or whatever. In other words, so this only works for 0 to 1. Okay. So what if it's something else? Well, what we're going to do here, if it goes from 5 to 9, the first number is a. That's what's important. The leftmost number is a. See, a to b. So the first, it's this. And the last number is, the left hand is the increment, which is b minus a over n, subtracted from the number. In other words, this is 1/10. 1 minus 1/10 is 0.9. So that's what we're doing here. So this is a way to write it for any a to b. Okay. But that's still right cumbersome to write out. B minus a over n. B, it's hard, even it's hard to type it up, you know. So what we're going to do is we're going to say, let's name b minus a over n. Let's call it delta x. Just give it a name. It makes sense, delta x. Delta means change in x. And this is what b minus a is. The a and b are x's, so it's a change in x, is it not? So that makes sense. B minus a over n, we're going to call delta x. And what we're going to do is come up here, and everywhere we have a b minus a over n, we're going to substitute in delta x. So we put it here, that gives us that, and we put it here, and that gives us that. We'll refer to this later. Okay, we're going to leave this for right now. And now we're going to approach the same problem we just did, but without a lot, is nowhere near as much verbiage because it's almost the same. We're going to do the same thing with the right-hand method. So this is what the right-hand method does. Now, the right-hand method doesn't start at 0. It starts 1 over from 0, 1 increment over. And it goes up to form your first rectangle, which is this. In other words, you come back. There's a rectangle. There's a rectangle. There's a rectangle. And so on. And we get to 1, and we have this rectangle here. Now, so the important thing you remember is for the right-hand method, you use the rightmost number and not your leftmost number. For the left, you use your leftmost number, but not your rightmost number. Now, if you'll notice here, everything is hanging outside of the graph. So when we do this problem, we should get an overestimate. Okay. So let's go to the next slide. Now, all we're doing here is the same thing we did before, but before, you remember, we started at 0 and went up to 0.9. We're starting at 0.1 and going up to 1. And all we do now is put each of these numbers into the function. We square it and add 1, square it and add 1, square it and add 1, square 1, which is 1, and add 1, 2. Add these up and multiply by the width. These add up to be 13.85 times that. Move the decimal 1 place back, and there's your answer. This is an overestimate. Too big. Keep that in mind. One of them is too big. One of them is too small. Now, I want to pause for a minute. We may address this again later. I don't want you to think that the right-hand method is always an overestimate. It is here. And that the left hand is always an underestimate. It is here. It's because it's an increasing function. If it's a decreasing function, in other words, the slope is negative as you move from left to right along the x-axis, then everything flips. Okay, the overestimate becomes the underestimate and vice versa. That's just a point of information for you to incorporate. Now, a shorter notation for the right-hand method would be this. In other words, we don't start at 0, we start one increment over. And we end where? At 1. So this would be the setup of it, the problem we just did. But again, just like before, we won't spend a lot of time. What if you don't have to have 0, 1. What if you had, like I said before, something like 5 to 9 or whatever? Then this would do it. A is your first number. So, and you go over the increment. In other words, you don't start at the leftmost point, you go over one increment and you end at your rightmost point. And just like before, since we said delta x is b minus a over n, let's go here and everywhere there's a b minus a over n, let's put delta x. And so this is pretty much a generic way for any AB to write this notation. And this notation is going to be, or a form of it is going to be very important to you as you journey through calculus. Now, if we increase the number of rectangles, two things happen. The left hand and right hand answer get closer to being equal, okay? The left and right hand answers get closer to being equal. If you increase the number of rectangles, the left hand answer and the right hand answer get closer to being getting the exact area. Now, as you may have figured already in your calculus study, the limits play a vital role in the development of calculus. It certainly did with the derivative. Remember, until you had the idea of limits, it took limits to get the definition of the derivative. Remember that formula? Well, likewise, limits is going to play a big role in what we're doing here. Okay, limits is going to play a big role. We'll see that before we get to the end of this lesson. Now, next is the engine that makes the antiderivative or integration, synonyms, a valuable tool. If we let n be very large, what we could say is that n is approaching infinity. In other words, infinity is as big as it gets. Well, if n approaches infinity, we write that n arrow infinity. Well, then that means the limit of b minus a over n as n approaches infinity is 0. But we said earlier that b minus a over n could also be written as delta x. So the limit of f of x delta x as x approaches 0 is another way of saying, let's pick an infinite number of rectangles. In other words, with delta x goes to 0, that says you're picking an infinite number of rectangles. Some people will write this as n approaches infinity and express this in terms of n, but we're choosing here to do it in terms of delta x, because delta x and the b minus a over n have a relationship, as we see here. And if you let n go to infinity, that's the same thing as saying let delta x go to 0. So just want to make sure, especially if you're observing this and you've seen other notation displaying this. Now, so this is most important. All I'm doing right here is indicating that this idea is very, very important. So we wanted to, before we left that, because it was tucked at the bottom of each of them, we want you to see that the one to the left and one to the right. So that's very important. You'll be seeing this again as you go through math, calculus in particular. Now, the left-hand method with 10 rectangles gave us 1.289, an underestimate. The right-hand method with 10 rectangles gave us 1.385, an overestimate. Well, let's take the average of those two answers. In other words, we'll add this to this, the too small and the too big. It seems like the exact answer should be somewhere in between. So let's just see what happens. I mean, that's kind of the way I would reason it, wouldn't you? So we're divided by 2 and we get this answer. So this should be a fairly good estimate. It's somewhere in between the two extremes right here. Okay. Now it's not exact. It's not exact. Why? Because we only used 10 rectangles. The more rectangles you use, the more exact it's going to be. Okay. Now, let's kind of shift gears here and let's try something. Remember that when it came to the derivative, you derived everything. So far with the antiderivative, you just kind of worked backwards and said, what gives you this, which gives you this? We did that way. We said if the derivative is a x cubed, what was the original? And it must have been x to the 4th. And we played around with that and we won't go into detail there. So let's play around with what we have here. Let's just suppose here, the antiderivative of f of x, you say, what's f of x? Well, any function. If the antiderivative of any function, little f, is capital F, in other words, these are not the same, right? The antiderivative of little f is capital F plus c. Well, what's our little f, by the way, for the problem we have? X squared plus 1. So what's the big F going to be? The antiderivative of x squared plus 1, which is what? X cubed over 3 plus x plus your constant of integration. Now, let's further play around with this. Let's see what happens if you put 1 into this. Well, what do you get? Well, you get 1/3, 1 cubed, plus 1 plus 4/3 plus c. What would happen if you put 0 into this thing? Well, you get 1/3, 0 cubed plus 0 plus c, which is just c. Now let's see what happens if you take the difference of these two. Well, you get f of 1, which is this, minus f of 0, which is this. Well, you end up with 4/3, or 1.333. What did we get when we just took the average of the two? Well, we've brought it forward for you. 1.337. This is 1.3333 on out. They're very close. Now, they would be closer if we'd used a number bigger than n. But we chose not to use a bigger than 10, an n bigger than 10, because we really didn't want them to come out to be exactly the same right here. Now, this is not a proof. I have not proven anything, but if you try this for any continuous function, now the function must be continuous, and in this case, an increasing function, we'll throw that in to cover all of that bases. I can show you that it's true every time, but I really don't want to go through that. I want to convince you otherwise. This is an expression of what we just went through there, which says if f of x is continuous from a to b, and the antiderivative of f of x is capital F of x plus c, then the integral from a to b of f of x dx is f of b minus f of a. In other words, if you integrate f of x and you get some capital F of x, if you put in your top limit and you put in your bottom limit and take the differences, these are the same things. Okay. Notice there is no c in this. Why? Well, we just saw the c's cancel each other out. So you don't see any c. And that's characteristic of a definite integral. There is no c. Okay. Indefinite integral, you have a c. A definite integral, you get a numerical answer, and there is no c. Something else to tuck into your thinking as we go through here. Let's take an example. Let's find, using this, the area under this graph. This is an increasing from 1 to 2. So what did the thing that just said? It said integrate this thing to find the capital F of x. Well, the integral of this is 3x cubed over 3. The 3's cancel, and 2x squared over 2, the 2's cancel, and 5x. And here this is momentary interruption here. We're hanging out numbers here. In other words, we don't want to go from here to here. It's too hard to do in your head. So we hang out little numbers here. Now we'll put in our numbers. We put in our top number, and what do? We do the arithmetic, get an answer. We put in our bottom number, do the arithmetic, and get an answer. And we take these and we do the arithmetic, gives you 22, the arithmetic gives you 7, and we subtract, we get 15, and there's your answer. That is the area under the curve. That's the exact. You say it's the exact. I know. Well, I told you, trust, if you did it a lot of times, it would. So we're doing it once. You said, but it doesn't, how do we really know that it's truly the area? Well, we're going to try to convince you in the next frame. Find the area under f of x equals 3x from 0 to 8. Let's graph that. That's 3x from 0 to 8. What is it? It's a triangle. What's the area of this triangle? Well, I know the formula is 1/2 the base times the height. Now my base is 0 to 8, so that's 8. And my height looks like it's 24. So 1/2 times 8 times 24 is the area of that triangle. Now, let's do it by calculus. Okay, you integrate. Well, you add 1, divide by the new exponent. You put in 8, you get an answer. You put in 0, you get an answer. You subtract the 2 answers, and you get 96. That's your answer. That's by calculus. Let's do it by geometry. Now we see that's 1/2 the base times the height. You do the arithmetic, they're the same. So this thing works for something that we know the area. In other words, this is not a close answer. This is the answer. Is that a proof? No, it's not. Would you use calculus to do this one? You could, but I don't know of anybody that would. If you saw that, surely you would say that's a triangle and get it over done with. No one would use calculus for that. I can't imagine anyway, unless they're, I just can't imagine why they would. Why are we doing it? To show you that the answer for a region you do know by calculus is the same answer you get it if you do it the tried and true method that you grew up learning about. Now let's take this region. It's a little more complicated. F of x is x minus 2 from 2 to 4. It's positive. And g of x is just 2 from 4 to 7. And h of x is negative 2x plus 16 from 7 to 8. Here's the graph. That's a trapezoid. You could look at it and say, this is a triangle, get that area. This is a rectangle, get this area, and this is a triangle, get this area. And that's, you're free to do that. This is also a trapezoid. So we're going to treat it as a trapezoid just because we don't use the area of a trapezoid formula often. A rectangle is nothing more than a special trapezoid where the opposite sides are the same, and of course you have the square where all the sides are the same. So trapezoid is a rectangle is a kind of trapezoid. But at any rate, I digress too much here. The area we'll tell you of a trapezoid is 1/2 base 1 plus base 2 times the height. Now the height of this thing is 2. And this base goes from 2 to 8, that's 6. And this goes from 4 to 7, so that's 3. So we can find that area. But let's do it by calculus. We take the first function from 2 to 4. And then the second function, which goes from 4 to 7. We'll do it piecemeal. And the third function, 7 to 8. And we'll integrate these. This is going to be x squared minus 2x. And we've got to do it from 4 to 2. And this is going to be just 2x. We'll do that from 2x. I'm sorry, I got too far over here. This is 2x, and that's from 7 to 4. And this is the integral of this. Then we do it from 7 to 8. Okay? We do it from 7 to 8. And this is what we get when we integrate each of these. This one gives us 2x, and this gives us minus 2x squared over 2, which is minus x squared and a 16x. And we just plug in and we get answer 9. Now, if we find the area of that trapezoid, remember we said it's 1/2 base 1, that was 6, lower base, base 2, the upper base was 3, and the height is 2, and you get 9. So it checks out here. So we're going to rest on this until somebody can disprove us that we are finding by calculus the exact area, not a close area. Now, we probably, if we had gone to our first one and maybe made 100 or 1,000 or whatever, n had been that, and we'd had that many rectangles, maybe that would have convinced somebody, but I'll leave that for someone else to do, not myself. Okay. Now, so we want to leave you with this, and that is, anytime you see this, limit as delta x approaches 0, the sum of the f of x sub I delta x, this means the integral of this thing evaluated from A to B. This is called the definite integral because we're going to get a numerical answer. There's no C there. As I said before, some text or instructors will do this in terms of n approaches infinity. It means the same thing. So don't, the main idea is, hopefully, as you journey on in mathematics, you will understand that this is what, when you come to this, you get this. Your instructor will get here and say, this means, as you remember, as you were told before, this, and move on without a lot of fanfare. So we're basically through with this. Our whole idea was to show you that when you integrate a function between its limits, and if it's a positive function that is above the x-axis, that's going to give you the area under the graph. It gives you a lot more too. So we're just, we're not going to explain here all the uses of the antiderivative or the definite integral in this lecture, but hopefully this, you will think over it, play it again if you need to, and you'll find it helpful.